Hey guys, welcome back to our fourth episode in our genetics series. If you haven't checked out our previous episodes, please do so by clicking the link somewhere around here to the playlist. I'll insert it somewhere on the screen. But definitely check them out first, guys. Today's video, we're going to be looking at codominant mutations. What are they? How do they work? Or more correctly, incomplete dominant mutations, and what does that actually mean? So, without ado, let's get started. So guys, today we're going to be taking together all the stuff we've learned over the last 3 episodes in this genetic series and applying it to ball pythons, applying it to the genetics in ball pythons. So we're going to start off today by looking simply at codominant mutations. Now, the hobby does refer to them as codoms, right? Or codominant mutations, where in fact they're actually incomplete dominant mutations, which basically means that an incomplete dominant mutation, if it only has one copy of a gene, it has a visual appearance, right? So we can visually see it because it is dominant. However, when you have an animal that carries 2 copies of that gene, it's almost like the full mutation shows through. It has what we call in the hobby a super form, or what we should know now as a homozygous form. So we're going to start by looking at a very simple gene that we work with here, and we're going to be looking at the fire gene, just as an example. So if we have 2 fire ball pythons, right? Let's say we have a fire female, okay? And we also have a fire male, and we want to breed them to each other to work out, and we want to work out what it is that it's going to create. Now, inheritance in ball pythons and the way genetics works in ball pythons is slightly different to humans. However, we're going to be using a very, very simple way of showing genes. So what we're going to say is the fire gene, okay, we're going to give it the genotype, because it's a dominant, a capital F for fire. And when an animal, such as a fire, only has 1 copy, we're going to say it has a normal gene, which we're going to refer to as N. So this female is visually, she is a fire ball python, and she has 1 copy of the fire gene, 1 copy of the normal gene. The same with the male. So we have a fire male, 1 copy of the fire gene, 1 copy of the normal gene. Now you realize that all of these are written in capitals. That's because normal, or the wild type mutation, is indeed a dominant gene. It's a dominant allele, and wherever a mutation occurs where it creates a different version, a new allele, it's actually changed a normal into, in this case, a fire. So we have a fire female breeding to a fire male, and we can quite easily use a Punnett square, as we did with the last video, to work out on average what we can expect from their offspring. So let's take this female and we'll draw our Punnett square as we did previously in our last episode, and we'll do fire 1 copy fire gene, or she could pass on the normal gene. Same with dad, could pass on the fire gene or could pass on the normal gene. And we can from this calculate how or what percentage of offspring would be fire, and so on. So here we have from the father an F, and from the mother an F, coming down F, coming across N, and then coming down N, coming across F, coming down N, coming down N. Now remember in the last video, guys, I said, see here we have NF and FN. They are the same thing, just written the other way around, but they are the same mutation. It basically means that either of these organisms have 1 copy of the normal gene, 1 copy of the fire gene. So let's have a quick look at what it is that we can produce from breeding a single gene fire to another single gene fire. So these 2 are the same, and we're going to write them as FN, same as the parents. So you can see there are 2 out of 4 here, so we have 50% FN, okay? So half of these offspring are gonna be FN heterozygous and they're gonna be fire. Visually, their phenotype are gonna be fire ball pythons. If we take this one next, NN, so 25%, 1 in 4, remember? 25% NN, we're going to have, they're going to be, this is obviously homozygous, 2 of the same. And so what we're going to have, visually, if it's got 2 copies of the normal gene, there is no fire here, so these animals are going to hatch out to be normals. And finally, we have this in the corner here. Now, with that, you have, again, 25%, 1 in 4, capital F, homozygous, because it's 2 of the same gene. And these are what, in the hobby, we're going to refer to as superfires. Whereas, in fact, all it is a homozygous fire animal. Now, where a lot of confusion comes from is when we're looking at these genes and we're not really understanding what's going on. So, for example, a lot of the time you will hear the term het, okay? So commonly you'll hear something like a het clown or a het pied. We will look at recessives in our next episode on their own so we can really split them apart. But here we're looking at het means, and if we look carefully, it means it has two different copies. Alternatively, you can think of het or heterozygous. So het is an abbreviated form of this word here. Okay, you could consider it as it has one copy of the gene you're interested in. So in this case, actually what we can refer to, what we generally in the hobby refer to as fire, could be considered to be a het fire, right? Because it's a heterozygous animal with one copy for fire. Whereas the superfire would actually be homozygous, so it would be the full fire ball python. Okay? And we're going to take a quick look now at what we mean or what we see with these genes. So, when we're talking about the heterozygous fire, an animal that has only got one copy of the fire gene, we are looking at this animal here. Visually, it's certainly different from a normal. It's much brighter. It has, it brightens with age. It has a little bit of a head stamp, and we have generally an animal that looks somewhat slightly different from a normal ball python, albeit it does improve with age. It does get even brighter with age. The idea is that a fire, a single gene fire, so this animal is actually a heterozygous animal which contains one copy of the fire gene and one copy of the normal gene. Now, unfortunately, we don't have any superfire hatchlings for this series just yet. However, I will show you what an adult looks like. So, when we get to adults, and bear in mind that this girl is a little bit dirty from her substrate, you get this animal here. So, if she, in her large, beautiful self, slightly moves out of the way, where we have this homozygous animal, a superfire as we call it in the hobby, it's actually homozygous. It has two copies of that fire gene, right? And this is the result. So when you have a homozygous animal, you have the full, so this female right here is carrying two copies of the fire gene, and this little one here is carrying only one copy. And you can see the difference between why we call them incomplete dominant. This is a slightly brighter than an average ball python compared to a normal. And then when you take it to the next level, when you add two copies of this light gene, you create what we call a superfire or a black-eyed Lucy. So an all-white snake for the most part with black eyes. And that's one good example of how codominant genes work. But what happens then if I want to breed a super ball python or a super fire, for example, a homozygous animal, to a normal? What are the chances of the offspring that I can produce? So now let's say we have a female right? For the sake of argument, we have that female superfire, capital F, breeding to a male who is a normal, and so has 2 copies of the normal gene. What could we possibly produce from this pairing? So if we do the same thing again, and we consider the Punnett square, we carry down the mother's genes, capital F and capital F, we carry down the father's genes, N, N, and we work it out, N, F, N, F, N, F, N, F. And you'll notice, because of this, you will have all of these offspring will give you 100% NF, which will in turn all be heterozygous, and therefore all be visually fireball pythons, just like the little one that was there previously. So when you breed a super to a normal, you are guaranteed, because the female must pass on one of these 2 genes, she has to pass on a fire gene to her offspring, and therefore all of her offspring would be fires. Now if you bred 2 supers together, you would notice, and if we just do it here in the top corner, if we kept the female the same as F, and we change the male to another superfire, then if you do a quick Punnett square, you will notice F, all of the babies will be superfires. And we're using fire here, so you get 100% FF homozygous super fire. And we're using this as an example here of a codominant, or in reality incomplete dominant mutation, which when bred can produce, in the case of a fire, right? In the case of 2 heterozygous animals, on average, half of the babies will be that heterozygous fire, as we saw previously. 25% will be superfire and 25% will be normal. In this case, where you're breeding a superfire to a normal, all of the hatchlings are guaranteed to will definitely inherit 1 copy of one of those fire genes from the female. Because she's a superfire, she has to pass on one of them, and therefore they'll all be heterozygous fire. If you breed 2 supers together, this would mean that all the offspring would also be superfires. Now, if you were to breed a fire to a normal, and we will change over and have a look at that. So, I just place this here. If we were to breed a female fire, right, so FN to a male, normal, then break down the female's genes. So let me draw the Punnett square first. Female's genes, F, N, N, N from the male. So here you got FN, here you have FN, here you have N, N, and here you have N, N. And you can see, if you breed an animal which has a codominant or incomplete dominant mutation to a normal, on average, 50%, right? 50% of all the hatchlings will be FN or FN heterozygous, which means they are fireball pythons. And the other 50% would be NN, homozygous, which are normals. Now, this is an easy way of looking at it when we're talking about a singular gene. But some of you may be asking, what would happen if you had combo animals? So let's say you had a fire pastel or a firefly, and you bred that to, hypothetically, a pinstripe, let's say. What could be the possibilities? Now that's where the Punnett square becomes too complicated to draw by hand, but you can still work out. All of those animals, all of those genes are individual to one another, so you'd have to draw a Punnett square for each of those genes for inheritance. But you could work out, on average, the pinstripe will pass on half of its genetics to each, or the pinstripe gene to each of its offspring. Half will produce or half of the offspring will receive the pastel gene from the other parent, and half of them will receive the fire gene. Now the combinations, that's where it gets a little bit confusing. However, that's where we have, well, the ball pythons have a really good genetic calculator, as do Morph Market, where you can input the genetics of your animals, and that will tell you what the possibility or what the percentage outcome for each possible offspring is.
So we just quickly Google search World of Ball Pythons calculator and click on the first link. That'll bring up this page. You can see here a box for the male, it says select male, and a box of female that says select female. So let's say the male is a firefly, which is a fire pastel. So we'll type in fire and we'll click on that. And then we'll type in pastel, and these are the two genes, and we'll click on that as well. You can then click on the female, in this case pinstripe, so we type pinstripe and click on that. And then you can, once you've inputted the female and male genetics, you can go ahead and click on calculate. This will bring up this menu below. So first of all, we'll show you pictures of the adults. Here it says firefly. Remember guys, that firefly is a generic name, or a common name if you will, for a fire pastel, and many of the ball python mutations or combinations out there have these sort of names. And this here, it would be the female pinstripe and a picture of her. If you go ahead and scroll down, you'll see a list of all the possible combination of the genes within the two parents. In this column you'll see fractions, and this one percentages, where you're actually looking at the percentage of each possible offspring. So between these two parents, you have a 12.5% chance on average of hitting, or 1 in 8 of hitting a pastel, and a 12.5% of 1 out of 8 of hitting a fire. Now, you have the same possibility here for all of these offsprings, but if we take a look at this 12.5 for the fire pastel pinstripe or dragonfly, also known as a fire lemon blast, and we click on that, that will actually take us to this little page here, where it has all the different images for that particular combination of mutations that's been produced by other people, almost like a picture log of what's here. But if we go back, it is important to note that these genes, this function doesn't always work. It is completely dependent on people submitting images of these combinations that have been made, and sometimes you'll find that it won't actually take you to a link. But this is the World of Ball Pythons page, the genetic wizard, and a real simple way for you to calculate possible offspring.
Right guys, I hope that video has really helped you work out how breeding different codominant and incomplete dominant mutations in ball pythons actually works, and how we can predict offspring from animals we already have that we know the genes of. The next episode will be up soon. Next episode will be on recessive mutations, so definitely check that out. Don't forget to hit the like and subscribe button. Leave a comment in the comment section down below, and until the next video, we'll see you then. Bye.